Welcome back. We are looking at notes for pre-calc for section 5.3 today. We'll handle most of the notes today and then finish up a little bit tomorrow. Our topics today deal with the sum and difference identities, and our objective is to be able to understand and use the sum and difference formulas for sine, cosine, and tangent. Wouldn't it be nice if every function followed this rule, that the function's value at a sum is the same as the sum of the two different functions' values? But we know this is not the case. For example, if we took u plus v, that quantity squared, it is not equivalent to the square of each one separate and then added together. Same with a square root, we can't split that apart. We are allowed to split apart a multiplication one. However, we cannot split apart a sum. All right. So for today, we're going to be using a lot of our main angles from our unit circle. So let's think about quadrant 1 and take a minute. You can pause the video, but I want you to put an ordered pair down for our main quadrant 1 angles. All right, checking a point here. We have the coordinates 1, 0. On the y-axis, our point is 0, 1. And then for 45 degrees, we have root 2 over 2 for both sine and cosine. For pi over 6, we have square root of 3 over 2 and 1/2. And for pi over 3, we have 1/2 and root 3 over 2. All right. So our first exploration, we're just going to show that we cannot split up this and take the sum, the sine of each one individually. All right. So it says let u be pi and let v be pi over 2. It says find the sine of u plus v and find the sine of u and the sine of v separately. All right. And we're looking for if they are equal to each other. So our sine of u plus v, and we said u was pi, so this would be the sine of pi plus pi over 2, or the sine of 3 pi over 2. All right, and looking at the sine of 3 pi over 2, we would be down here. Coordinates are 0, -1, so our value here would be -1. If we look at the other option, saying the sine of u plus the sine of v, we are looking at the sine of pi plus the sine of pi over 2. Well, sine of pi is over here. Coordinates are -1, 0. So the sine of pi is 0, and the sine of pi over 2 is 1. And if we add those together, we get 1. And so you'll notice that these two quantities are not the same. All right, so the sine of u plus v does not equal the sine of u plus the sine of v. All right, our second one says u this time is going to be 0 and v is going to be 2 pi, and we're comparing the cosines now. So let's take cosine of u plus v, which in this case is 0 and 2 pi, and we're looking to see, does it equal the cosine of 0 plus the cosine of 2 pi? All right, well, if we add 0 plus 2 pi, that's just 2 pi. And the cosine at 2 pi, which is back here at 0, cosine is 1. Over here we have the cosine of 0, which is 1, and the cosine of 2 pi, which is 1 again. They're in the same spot. And so on this side we get 2, and 1 does not equal 2, so these are not equivalent. All right, our third example, it says find your own values for u and v that will confirm that the tangent of u plus v does not equal the tangent of u plus the tangent of v. All right, so let's pick a couple values for u and v. And you have a lot of options. I would pick things that are on our unit circle to make things a little easier. Let's say that we let both of them, let's just pick pi over 3 for both angles. All right, so we're saying that is the tangent of pi over 3 plus pi over 3 equivalent to the tangent of pi over 3 plus the tangent of pi over 3. All right, well, if we take pi over 3 plus pi over 3, we've got the tangent of 2 pi over 3. Okay, so let's go back up here. Pi over 3 has coordinates 1/2 and root 3 over 2. Tangent, remember, is y over x. So we have root 3 over 2 divided by 1/2. And in this case, both of those 2's on the bottom drop out. We end up with the root 3 plus a root 3 or 2 root 3's. Okay, if we look at 2/3 pi for our other side, then we are over here, all right, and our coordinates are almost identical to the one I have circled in green here. However, when we flip it over the y-axis, our x-coordinate becomes negative. So we have negative 1/2 root 3 over 2. And so the tangent is going to be root 3 over 2 divided by negative 1 over 2. All right, the 2's drop out again, and we end up with a negative root 3. And those are not equivalent. So once again, tangent of the sum of two angles is not the same as the sum of the tangent of each angle separately. All right, so what can we do instead? We do have some identities for sum and differences. For sine, the formula is the sine of a sum, all right, the sine of u plus v, is equal to the sine of u times the cosine of v plus the cosine of u times the sine of v. And you'll notice that it's very, very similar when we do the sine of a difference. We have sine of u cosine v minus cosine u sine v. So there is no sign change for sine, right? So the signs stay the same when you're dealing with a sum of a sine, or sorry, the sine of a sum. All right, for cosines, the sign does change. So if you think of these two, okay, sign changes. If you have a plus here, you have a minus here. If you have a minus here, you have a plus there. That's what we mean by the sign changing. Now, for cosine, the formula says the cosine of u plus v is the cosine of both of them multiplied together minus the sine of both angles multiplied together. Okay? It says in order to use these formulas, we need to be able to write angles as a combination of our special ones. So we know our 30/60s, our 45s, our nice quadrantal 90, 180, that type of thing. So we want to look at how can we create these angles using some of our special ones. There are often many options, so if you can come up with some other ones, that's perfectly fine. Our first one, we're trying to create a 15-degree angle. Well, 15 degrees could be thought of as 45 degrees minus 30 degrees. And we know values for sine, cosine, and tangent of 45 and 30, so we would use that combination. 75 is just the sum of those same two angles. Okay. Now, 165, it's close to 180. If you think of it as 180 minus 15, all right, we know values for 180, and we've already looked at ways to represent a 15 here. Since we want it to be a minus 15, we can just flip-flop our 30s and 45s and make it 30 minus 45. So 165 would be equivalent to 180 plus 30 minus 45. Okay, again, this is going to be our negative 15 here. All right, and 180 plus 30 is 210, which is another one of our angles that we know on our unit circle. So we can think of 165 as the combination of 210 minus 45. Gets a little trickier when we deal with radian notation, just because we don't always have the denominators the way we want them. You'll notice all of these are denominators of 12. So let's go through somewhere on the side. Let's just go through and look at all the 12ths. Okay, so we have pi over 12, we have 2 pi over 12, but that reduces to pi over 6, and that is one of our known ones. We have 3 pi over 12, and that reduces to pi over 4. We have 4 pi over 12, which reduces to pi over 3. We have 5 pi over 12. We have 6 pi over 12, and that reduces to pi over 2. 7 pi over 12. 8 pi over 12 would reduce to 2 pi over 3. 9 twelfths reduces to 3/4. 10 twelfths reduces to 5/6. And 12 twelfths reduces to 1 pi. So you'll notice that most of our twelfths can be written as one of our angles on our unit circle. There's a few like 5 twelfths that can't, but we're going to look at how can we create that using combinations of the other ones that we know. All right, so again, there's multiple ways we can get an answer here. If I want to get, for number 4 here, pi over 12, I want 1/12, I can subtract two values that are right next to each other. For example, I could take 3 minus 2. I could take 4 minus 3. Those all give me a 1. So let's look at this as our easiest one. We would say is 3 pi over 12 minus 2 pi over 12. Or we could say that is pi over 4 minus pi over 6. And we know values for sine, cosine, and tangent of pi over 4 and pi over 6. Again, we also could have used pi over 3 minus pi over 4. Would also get us a 1/12. To get a 5/12, we need to look for numbers that are 5 apart and values that we know. For example, we could use an 8 minus a 3 here would give us a difference of 5, and we know both of those. So 8 pi over 12 minus 3 pi over 12, and we said 8/12 was 2 pi over 3, and 3 pi over 12 would reduce to pi over 4. So if we need to come up with sine of 5 pi over 12, we can use sines and cosines of the 2 pi over 3 and the pi over 4. All right, pause the video, and I want you to try to come up with a way to get 7 pi over 12. All right, to get a 7, we could combine a 3 and a 4 here by adding them together. So we can think of this as 3 pi over 4 plus, 3 pi over 12 and 4 pi over 12. All right, so let's try our first example here. It says using the cosine of a difference identity, find the exact value of the cosine of 15 degrees without using a calculator. Well, if we go back up here, we said 15 degrees can be thought of as 45 minus 30. So we're going to say the cosine of 15 degrees is the cosine of 45 degrees minus 30 degrees. Okay, and our identity that we have for our difference of cosines says that that is equivalent to cosine of 45 times cosine of 30 plus our sign changes for cosine. So we have a minus here, we are going to have a plus here, and then we have sine of the two. So sine of 45 and sine of 30. All right, and now we can just substitute values from our unit circle. We know the cosine of 45 is root 2 over 2, and the sine of 45 is root 2 over 2. And if we look at our 30-degree angles, we know cosine is root 3 over 2, and sine is 1/2. And now we just do our arithmetic. We've got root 2 times root 3, that's the square root of 6 over 2, over 4. And over here we've got the square root of 2 over 4. Now they both have a denominator 4, so we can simplify that and say it's root 6 plus root 2 all over a single 4. That would be our most simplified answer for that. All right, let's shift to example 2 here. It says to prove the identities that the cosine of the complement is equal to the sine of the original angle, and the sine of the complement is equal to the cosine of the original angle. All right, so let's work on the first one here. We have the cosine of pi over 2 minus x. So we're looking at the cosine of a difference, which is the cosine of each one. And we change the sign, so plus, and then the sine of each one. Okay? And substituting in the cosine of pi over 2, that's 90 degrees. We're on the positive y-axis. Our cosine is 0, and our sine is 1. We don't know sine and cosine of x, but we can simplify this down. 0 times anything is 0, which leaves us just with 1 times sine x, or sine x. And we have proved what it is supposed to be equal to. All right, part B says to prove that the sine of pi over 2 minus x is equivalent to the cosine of x. So let's break this up using our identity. We have the sine of a difference, and with sines, the middle sign here does not change. So we are going to have a subtraction. And the formula says to take the sine of the first one times the cosine of the second one. And we change the sign so it becomes, sine does not change, minus. And then we take the cosine of the first one times the sine of the second one. All right, simplifying, at pi over 2, our sine is 1, so we get 1 cosine of x, minus our cosine at pi over 2 was 0, and 0 times anything is 0, so this ends up being just cosine of x, which again is what we were trying to prove. All right, for example 3. It says write each of the following expressions as the sine or cosine of an angle. So now I'm giving you the broken apart version, and I'm asking you to come up with what was the original question. All right, so it is a sine times cosine plus cosine times sine. When you have one of each, that is a sine formula. Okay, and because it's a plus here, we know we're adding here. The signs do not change for sines. And we are simply adding the two angles. So we have a 22-degree angle and a 13-degree angle, which means we're really just saying, what is the sine of 35 degrees? Okay. For part B, it is a cosine, cosine plus sine, sine. That is a cosine formula. The sign does change. Cosine changes sine here. So if it's a plus here, we're going to have a minus here. And we need cosine of pi over 3 times cosine of pi over 4. So our two angles are pi over 3 and pi over 4. Now we want to be able to simplify that, so let's convert those into twelfths again. Pi over 3 would be 4 pi over 12, and pi over 4 would be 3 pi over 12. So this becomes the cosine of 1 pi over 12. All right, pause the video and I want you to try this third one here on your own and then turn it back on when you're done. Okay, so this one was a little trickier because normally in our formula we have cosine, cosine, and then sine, sine. In this one, it's switched around. But what if we change this and wrote this as negative cosine x, cosine 2x, plus sine x, sine 2x. So we have it kind of in the right format. And then let's get rid of this negative in front. Let's factor it out. makes this a minus sign here. Okay, so now it's looking more like one of our identities. We have cosine, cosine minus sine, sine, which is a cosine formula. And for cosines, the sign changes. So if we have a minus here, we're going to have a plus here. And the two angles that are being used are an x and a 2x. So this turns into negative cosine of 3x. All right, we have one more example. It says if one of the angles in a sum or difference is a quadrantal angle, that is a multiple of 90 degrees or of pi over 2 radians, then the sum and difference identities yield single-term expressions. Since the effect is to reduce the complexity, the resulting identity is called a reduction formula. So you'll see some reduction formulas as we continue on in trig. This one is asking us to prove the formula that the sine of x plus pi is equal to the opposite of the sine of x. So let's go through our sine of a sum. Okay, the sine of a sum is the sine of the first one times the cosine of the second one. Okay, and the sign stays the same. Sorry, sign stays the same. And then we have the cosine of x and the sine of our second one, pi. All right, and again, looking at pi over here, our coordinates are -1, 0. So the cosine is -1 and the sine is 0. All right, so this drops out and we end up with negative sine x, which is what we were trying to prove. Okay, so I want you to try that with this one. Go ahead and pause the video and turn it back on when you are done. All right, so the cosine of x plus 3 pi over 2, we are looking at the cosine of a sum. So we have cosine of both, and the sign changes for cosine. So if we have a plus here, we're going to have a minus here, and then we have the sine of each one. So sine x and sine 3 pi over 2. And simplifying, at 3 pi over 2, we are down here. Our coordinates are 0, -1. So our cosine is 0, and our sine is -1. And this cancels out, becomes 0. We end up with a negative times a negative, which gives us a positive sine x. Again, getting what we were asked to prove. All right, so we're going to have you try some of those. The assignment is all listed as 1, and what I need for you to do on day 1 is skip all of the ones involving tangent. We'll talk about how to do a tangent formula tomorrow. So skip the ones involving tangent. All right, we'll handle those tomorrow.